Okay, so we're going to continue doing some like supersaturation stuff. If we kind of recall also, well, like a supersaturation problem. The idea is we suppose G has n vertices and the number of edges in G is a lot bigger, where a lot bigger maybe changes depending on what we're proving, but a lot bigger than the extremal number. And then we want to know how many copies of H must G contain. And it's always got to have at least one copy, but we want to like get a quantitative bound on that. I also want to recall this thing pi of H, which we call the Turán density. Because the theorem we're going to prove today is involving this pi of H. So yeah, what we're going to prove is something, a result of Erdős and Simonovits. So it's sometimes called the Erdős-Simonovits Supersaturation Theorem. So just to kind of go back a second, what we've done so far is we've like looked at triangles and we got some very specific bound, which which is actually tight for infinitely many edge densities. So it's not always tight, but it's usually tight, or not usually even, but often tight. And then we did some stuff about even cycles, but we haven't really addressed like what about any graph H, right? So that's what I want to do here. And but the bound we're going to get is not as precise as those other ones. Those ones were like, at least they were tight. They were often tight, but this one's not going to be. But it gives us a rough idea. So for any graph H with at least one edge. Otherwise, all of these problems become not really well defined in some sense. And any epsilon, real number that's positive. There exists a constant C depending on H and epsilon. So some positive constant. Such that, well, and maybe I'll also define another constant. Some natural number n naught. H and epsilon, such that if G is a graph with, let's say, n vertices where n is at least n naught, and at least pi of H plus epsilon, n choose two edges, then G has at least C times, so this is the same C, I'm just not writing the parameters here. So C times n to the power of the number of vertices of H copies of H. And we've kind of talked about what do I mean by a copy. Like this has been a thing that we've had to kind of discuss. Like, am I talking about homomorphisms? Am I talking about, I don't know, just unlabeled copies? In some sense, though, here it's not going to matter at all because kind of no matter if you have any kind of reasonable notion of what a copy is, it's not going to matter whether we're talking about homomorphisms or unlabeled copies. Because, I mean, the number of copies we're getting is n to the v of h. So, I mean, if I've got that many homomorphisms, for example, you could say, okay, some of them might not be injective, so some of them may not be actual copies, but the number of non-injective ones is at most n to the v of h minus 1 times a constant. So like, in some sense, the true copies are going to dominate no matter what you're talking about when you're doing copies. So we're going to be a little bit relaxed for this theorem when I talk about what is a copy. Okay. Any questions about this statement? It's a bit of a long statement with a lot of quantifiers. But basically what this is saying is if the number of edges is even a little bit larger in terms of like the constant factor, like because the extremal number is going to be kind of like pi of h times n choose 2, kind of. And if the number of edges is significantly bigger than that by some little, I mean even just some little constant here, then all of a sudden you don't just get one copy of h or a small number of copies of h, but you get like a positive percentage of all the possible copies of h in your graph. Okay. One kind of interesting thing about this proof is we're not actually, so we actually know what this number is. Like for any graph h, this is just chromatic number minus 2 over chromatic number minus 1. In principle, you could imagine in this proof we could use that fact. Like we could use the Erdős theorem and use the fact that we actually know this number. But we're not even going to do that. We're just going to say implicitly, like this number is just, it's this limit, whatever it is. I don't even care that there is an Erdős theorem, and it's going to work even for that. So, and that's kind of interesting because if we have time afterwards, I'll use this theorem to reprove the Erdős theorem again. So, so we're not using the Erdős theorem to prove this. Okay, so so by definition of the Turán density, I can let let's say M be large enough that the extremal number exnh is less than pi of h plus epsilon over 2 times n choose 2 for all n at least m. Okay. And this is just by definition of the Turán density. Right? It's defined to be the limit. So eventually, you know, this number is going to go below, like this, the ratio is going to go below that quantity, and then it's going to, it'll never go above that quantity again. I mean, eventually that's going to happen, right? Because just by definition of what taking a limit means. Okay. Okay, so, and actually I I mean, I think actually this m is going to end up being my n naught. But so here's the idea. So now take a graph on n vertices. And so n is some large number. Take m vertices out of that n. If among those m vertices, if there's a lot of edges, if it has density kind of bigger than pi of h plus epsilon over 2, you're going to find an h in there. Like if this set of vertices has too many edges, you will find an h in there just by this thing. And so, I mean, imagine every set of m vertices had like too many edges. So we would find kind of a copy of h in every possible set of size m. That would then, of course, like in some sense, it looks like then we're getting kind of n choose m copies of h, but we're not actually, because you may count a copy twice, right? So if this is a copy of h that I found within those m vertices, I'll also find the same copy of h within these m vertices, right? But basically, any way of choosing these m vertices, I would find a copy of h, and then I would say, oh, well, any given copy of h is only counted like n minus number of vertices of h, choose m minus the number of vertices of h times, right? Because if I have a given copy of h, how many times could I have counted it? It's the number of ways to choose the other vertices in that set of size m. And this is kind of like n to the m over n to the m minus v of h so technically up to some constant factor, right? Where m I'm just treating as a constant. Like m is a fixed number, and n is now growing way beyond m, right? And so this would be kind of n to the v of h copies. But there's a problem with this argument because I don't actually know that every single possible set of size m has too many edges. There could be some sparse sets and some dense sets. But if I can show that a positive proportion of them have too many edges, then I would win. Okay, let's make this more formal. So let D be the set of all subsets of the vertex set of G such that the size of S is M. And so I'm just going to write like little e of S just to mean the number of edges within S. So this number of edges is, let's say, at least pi of h plus epsilon over 2, m choose 2. So the reason I'm using D is because I consider these to be my dense sets. Okay. And by the way I chose M, every set S and D contains a copy of H. Okay. Right, because it's got more than the extremal number of edges for M vertices, right? Okay, and then kind of like I was saying here, like the number of copies of H will just be the cardinality of D divided by this thing which considers the overcounting. And as long as we can show that the size of D is like something like D to the or n to the m times a constant, then we're going to be happy. So let's bound the size of D. So we want to lower bound the size of D, because basically, if we can show that there's a lot of dense sets, then that's going to translate to giving us a lot of copies of H. The way we're going to do this is kind of, yeah, kind of almost a little silly, but basically this is going to come down to using the fact that, like here we put it like an epsilon over 2, which gives us a little bit of wiggle room in the sense that, like if I took, for example, like a random set of m vertices in the graph, like the whole graph has pi of h times, or pi of h plus epsilon n choose 2 edges. If I took a random set, I would expect the density to be like pi of h plus epsilon over epsilon. And this kind of density thing is only saying, all you need is epsilon over 2. So that's sort of going to help us. So anyway, so let's say, I'm going to maybe just start using E of G for the number of edges of G. So okay, we know this is at least pi of h plus epsilon n choose 2 by hypothesis. And we can also upper bound it. So I want to count the edges by counting, like by going over all the sets of size m and saying how many edges are in that set. And if it's a dense set, it might have a lot of edges, but if it's a sparse set, it's going to have few. So, so if I go over all the sets of size m and I count the edges within them, that's going to overcount the edges, right? Each edge will be counted something like, well, in fact, exactly n minus 2 times, or n minus 2 choose m minus 2 times. So I'm going to put that on the bottom. So is it clear what I'm saying here? If I sum over all sets of size m and count how many edges are in it, a given edge will be overcounted. And the number of times it gets counted is the number of ways to choose the other vertices. And then every time I have a dense set, I can't actually say much about it. It could just be a clique. So I'm going to just write m choose 2. And every time I have a sparse set, of which there are n choose m minus the size of d of them, well, it has to have less than pi of h plus epsilon over 2 m choose 2 edges. Okay. So yeah, the numerator is just going through all the sets and upper bounding the number, all the sets of size m, upper bounding how many edges it could have. Right. Okay. So now let's solve for D. right? So we've got this lower bound, this upper bound. So, okay, so I'm going to multiply both sides by this. And here I've got size of d times m choose 2. Actually, both of my size of d's have like an m choose 2, and then I've got like a 1 minus pi of h minus epsilon over 2.
On the left-hand side should just be epsilon?
Yeah, thanks. Yeah, that would mess everything up, so we need that epsilon. Thanks. And then I've got some extra stuff, which is n choose m, m choose 2, I think, and then times pi of h plus epsilon over 2. Here's a nice thing, nice combinatorial thing. These numbers are the same, I think. Is that right? I've got n, imagine I've got n objects. I'm going to color 2 of them red, and I'm going to color m minus 2 of them blue. This way I'm saying, first I say, okay, I've got my n objects, I pick 2 of them to be red, and then from the remainder, I pick m minus 2 of them to be blue. Like this is now I've kind of removed my red ones, and now I'm picking m minus 2 blues, right? This is saying, and this one's saying, I've got my n objects, I'm going to pick the m colored things without telling me what color they're going to be. And I'm going to pick among those m things, 2 of them to be red, and then I'll just make the rest blue. Right, so these are the same thing, which is good because I wouldn't know how to do this otherwise. So yeah, I can just kind of put everything over there. So yeah, just replace this literally with the other thing, right? N choose 2, n minus 2 choose m minus 2. They are the same, right? Move things to the other side. And what I've got over here is an epsilon over 2. So this is where we got this little bit of slack. Choose m minus 2. And then, yeah, over here we've got this thing. So let's now actually divide as well. So m choose 2, 1 minus that. And maybe at the beginning of this whole thing, we should have probably said that epsilon is small. Otherwise, I mean, I don't want to have a negative number here or a 0 or something. Like, of course, if this theorem holds for small epsilon, then it also holds for larger epsilon. So, so maybe kind of this should have probably been mentioned at the beginning, but we can assume, for example, epsilon is less than, it's smaller than whatever we want it to be, right? So therefore, this thing is going to be positive. Because the Turán density can never be 1, I guess, but yeah. Okay, so this actually gives us kind of what we want. So let's kind of think about what this is giving us in terms of a function of n. So so remember, so m is like a fixed number. We just choose m big enough so that this thing holds. And that's just a fixed number depending on epsilon and h. And then we fix it, and then we let n be really large with respect to m. So yeah, what we're getting here is that this is at least, this is kind of like an n squared. Well, so maybe I'll write this in asymptotic notation. So it's omega. Omega means at least a constant times. That's like an n squared. This thing is like an n to the m minus 2. And this thing on the bottom is just a constant, because m is just picked with respect to epsilon and h.
Why don't we write it as n choose m and m choose 2, because then you can cancel it?
Yeah, that might be nice as well.
Is there a reason we want to leave it the other way, or does it matter?
Doesn't matter, yeah. These things are the same thing, so if you wanted to write that one, you're right, it does like cancel it and makes it look a little bit prettier, but at the end of the day, it doesn't actually matter. But yeah, you're right, that would be more elegant. But in any case, the main kind of message is that the number of dense sets is like n to the m. And then to finish it, we just do this kind of argument we had before. So just to do that a bit more properly, so number of copies of H, no matter how you want to define copy, it doesn't really matter. Every dense set is going to have at least one of them, but this overcounts by a factor of n minus m n minus number of vertices of H over m minus number of vertices of H. Because again, when I find a copy in one set of size m, I'm going to be counting that copy many times. And yeah, this grows like n to the m over n to the m minus v of h. So like in total, it's n to the v of h. So there does indeed exist a constant where the number of copies is going to be that constant times, at least that constant times n to the v of h. Okay. So one nice thing about this argument is that it's not actually really using very much. Like it's a very it's not using anything about H. I mean, it's just using how numbers work, maybe. Like, so let's see how this implies the Erdős theorem. So this thing that we spent 2 lectures on earlier, we'll just do it in like 20 minutes, or even less, maybe. So we're going to prove it in that sort of sense of like finding a complete multipartite graph, because that we've talked about that sort of reduction before. So I'm going to prove that for any r at least 2 and t at least 1 and epsilon positive, there exists and not depending on r and t and epsilon, such that if n is at least n naught, then the extremal number of this complete multipartite graph with r parts, all of size t, is less than or equal to t minus 2 over t minus 1 plus epsilon n choose 2. I think this is the same statement. So actually what we're going to use for this is two things. We're going to use the thing we just proved, the supersaturation thing, and we're going to use Turán's theorem. Okay. So by Turán's theorem, we know that the Turán density of a complete graph. Oh, sorry, I messed this up. This is not supposed to depend on t. It's supposed to depend on the number of parts in the multipartite graph, right? It depends on the chromatic number. That should have been r minus 2 over r minus 1. Yeah. So yeah, by Turán's theorem, we know that the Turán density of Kr is r minus 2 over r minus 1. In fact, we know the exact best construction for every n, right? You take a complete r minus 1 partite graph with parts of size roughly equal, right? So if we combine this with this supersaturation theorem, if G has n vertices and more than r minus 2 over r minus 1 plus epsilon n choose 2 edges for large n, then it contains a constant multiple of n to the r copies of Kr. So here this implicit constant, the constant depends on r and epsilon, I believe, right? So this is just by the supersaturation theorem that we just proved. Okay. So what we've done is we're kind of saying if you've got a large graph which is kind of too dense, like overly dense kind of by a little bit, then you're going to get a lot of KRs. And now we just kind of want to use that to get a lot of copies of this graph. And in particular, we want to get at least one copy of that graph, right? If I can show that such a graph will also contain one of these, then I'm done, right? That means that the extremal number of this is less than that value for large enough n. So I sort of want to take lots of KRs and use that to get lots of complete multipartite graph things. So it's a little bit complicated to do this kind of notationally, but so let me kind of invent on the fly some notation, and we'll see how it kind of relates to this. So so given a graph, essentially what I want to do is I want to, for example, if R is 3, I want to use that you've got a lot of triangles to give me a lot of graphs, a lot of copies of this graph where I've kind of cloned that one of the vertices of the triangle t times. So if you have a lot of these, I want to get a lot of these. But then if you have a lot of these, I want to get a lot of the graph where I clone this one a lot of times. And if I have a lot of those, I want to be able to clone this one a lot of times. But sort of after the first step, I'm not dealing with cliques anymore, so I don't want to. So anyway, I'm going to say, given a graph H, a set, let's say, a set of vertices and a map psi from S to the vertices of G. Let's say hom sub psi Hg be the number of homomorphisms from H to G that extend psi. And what I mean by this is we're looking at homomorphisms where if I restrict, we're counting homomorphisms phi where if I restrict to S, I get psi. Okay. Of course, if there's some edge within S, and this psi function maps that edge to a non-edge, then there are just no homomorphisms that extend it, right? Because it's already violating the homomorphism condition. So really, so it'll be 0 in that case. But more generally, like if the restriction of psi to S satisfies the homomorphism condition, this will count the number of extensions to the rest of the graph. So the point of this is if I sum overall, so let's say the vertices so let's say that the vertices of Kr are the numbers 1 up to R. If I sum overall psi, which maps 1 up to R minus 1 to G, V of G, and I take this quantity, well, that just counts homomorphisms, right? Because it's just kind of separating over cases based on where do the first R minus 1 vertices map.
Is it H that we're looking for?
Yeah. Let's call it HKR for now. Yeah. But later I'm going to want to apply this to other graphs because I'm going to want to apply it to this one and then the next one and so on. But yeah, you're right. This is KR. Right? Because if I want to count a homomorphism, the first R minus 1 vertices must go somewhere, and I just sum over all of those somewheres, right? And since I've got a lot of copies of KR, in this case, copies and homomorphisms are kind of almost the same thing, right, for KR. So yeah, this is going to be at least, well, right? So if I want to count copies of this thing, where I've got where I've cloned that vertex t times. And okay, sorry, make this a set of size r minus 1. And clone the rth vertex t times. If you think about it, this is the same as summing overall psi from 1 to r minus 1 to the vertices of G, and taking the tth power of that quantity. Right, because if I wanted to get a homomorphism of this graph, what I first need to do is kind of map the r minus 1 vertices in this clique via a homomorphism. And then if I think of how many extensions there are to that last vertex, if I kind of take that to the power t, like that's going to correctly count the homomorphisms. Right, because basically, yeah, these things are clones of each other. Is it clear why this should be true? So, okay. We can now use like Holder's inequality. And actually, I'm going to sort of restrict this sum to only deal with the things which are homomorphisms from which actually preserve edges. So phi is a homomorphism from kr minus 1 to G. And we can do that because all the other terms are 0, right? If phi maps an edge to a non-edge already, or sorry, psi, then there are no extensions of that to a homomorphism. So we may as well just sum over the good ones. So if I apply Holder's inequality, what you get is this is at least the number of terms of this sum, well, 1 over that to the t minus 1 times the sum of these things with no power, just power 1. And then you take that whole sum to the t. And this whole sum is just what we had before. It's just the number of homomorphisms of kr to G. So that's like n to the r. This thing here, the number of homomorphisms of kr minus 1 to G, it couldn't be bigger than n to the r minus 1. Even if G is a clique, this is going to be like n to the r minus 1. So
Sorry, Joe, what's the last sum over?
oh, this is over the same thing. So some maps from 1 up to r minus 1. Yeah, although in this case we could drop that restriction if we really wanted to because it won't change it, but we may as well. So like I'm saying, like this part's notationally really annoying, but so anyway, so what we're getting is so that's at least so here I'm just saying in the worst case, every single map could be a homomorphism from kr minus 1 to G. Of course, it can't be true, but, well, actually, sorry, I'm going to need a constant here. So there's an omega here again. And then I've got n to the r to the t. What on earth does this give me? The RTs cancel. Can anyone verify this algebra? Yeah, that looks right, I think, right?
Yeah, that's right.
Which is, like, very conveniently, it's like n to the number of vertices of this thing. Well, I don't really know how to write that, but, and I guess if you wanted to now, like, finish off this proof, so maybe I won't do all the details, but you would just do this again. You would say, okay, now what I'm going to do is I'm going to look at all the maps that fix every vertex of this graph except for one of the ones down here in the clique. And sum over all those possibilities. And now if I sum over all those possibilities to the power t, that's going to be like cloning that last vertex t times. And you can kind of take my word for it that the numbers are going to work out, and you're going to get n to the power of the number of vertices of that new graph. And then you just keep doing this and doing this. As you keep doing this, this constant factor gets worse and worse and worse. Like every step we do this, it gets raised to the power t or something, or maybe even worse than that. But at the end, you do this finitely many times, and you've got some constant here times n to the power of the number of vertices. So basically, if I keep doing this, I'll get this many n to the RT copies of k tt dot 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 t, where I've got r of them, r parts. So anyway, so it's just using this Holder's inequality over and over and over, and yeah. Okay, so sorry that was a bit sloppy at the end. It's notationally really annoying to write this, but hopefully the idea kind of makes sense. This is not even written in the notes, so you don't have to worry too much about this, but yeah. Any questions about this?